Okay, everybody, so today we are building our knowledge of more advanced shell coding techniques. This will build off of some of our previous videos, such as the basics of shell coding, the PE file format, walking the process environment block or the PEB, as well as walking the PE file format. If you have not watched those videos, if you have not understood those materials, then it's time to go back and revisit those videos. It's not optional to understand that content. That content simply needs to be well understood in order for you to make sense of what we're doing today. Not only that, but to be able to do it yourself. Now that said, you certainly don't need to understand all the intricacies of the PE file format, but you should understand enough of the PE file format that you're able to follow along and get the gist of our last video where we walked the PEB and walked the PE file format. Today, we are taking some of those ideas, some of those concepts, and we are utilizing them in a slightly different fashion. So we're walking the PEB, we're walking the PE file format, but we're doing it in straight shellcode, which we will then turn into binary content, and then we can then use that or inside of our exploits. And that will be something that you will do in your own labs. So again, what we're doing here is similar, but it's a little bit more advanced. It's broken down into, it's very modular, so there are different function calls inside it, and that's fine. We can certainly make use of that inside our shell code. But you need to really understand some of the basics just to be able to make sense of this. We're also using hashing. So hashing of different module names, different APIs is something that we do to make our code a little bit more challenging for people to decipher. So if somebody were to encounter the shellcode and they didn't know how it was encrypted, then they may not be able to successfully decrypt it. So we do have some hash tables, and we can see them in play down here. Now I'm going to give this to you as a skeleton. So everything here you will have a copy of. I will show some additional shellcode that I will not give you a copy of. So if you feel like taking notes, feel free. There is a pause button, of course, on the videos. So I would encourage students to make use of the opportunity to take notes. But as far as this, of course, if not necessary, you will have access to this code. But there are some to-dos that you will need to complete. And all this does really is it enables you to load modules if you need to load modules, and additionally to get the API address of functions. That's just a starting point. So once you get all this done, then you actually need to make use of those functions, to call those functions, and to if necessary, chain them together such that you do something meaningful, something significant. So that is the task ahead of you. And we'll go over this in detail and show you some examples. So don't worry about not understanding right at this point. So again, all of this really harkens back to that idea that we need to make use of walking the PEB, traversing the PE file format in order to get API addresses of functions when ASLR, address space layout randomization, is in place. And even if ASLR was not in place, that's actually irrelevant, so I probably shouldn't have even said it. It goes to the idea of shellcode being position independent. You get your shellcode. The shellcode doesn't know where any of these libraries are or where any of these functions are. So we use these techniques in order to get the addresses. So this is the same exact technique that we had in our last video. It's just been made modular by having different functions as well as labels within the shellcode. So a little bit more sophistication as far as shellcode. And then making use of hashing. So if we do hashing, then it can be a lot easier for us to collect the addresses. There are a number of different APIs. It can simplify things. So we'll see how that's done. Now once again, and we haven't really started to talk about this yet, but this is the skeleton that allows us to get that information. So we'll populate it with the appropriate data, and this will enable us to make sure those modules are loaded if they're not already loaded. So we can use load library as a mechanism to load a module that's not going to be loaded. And then we can get the API address. See that funny little guy right there? He'll help us get that. And then there'll be an opportunity here where we can call our API. So if we go through, make use of the hash table, get an API address, then we can call that API address. You know, if you're really clever and you understand assembly well, you could even store that API address on the stack at a place so you could reuse it later on. I don't require that, but that's an option if it's necessary and if you want to. And then when this completes, then if you needed to load a different module or get addresses from a different hash table, then you could do so, and then you could call that one. And we'll see some tangible examples of that. And when you guys get done with this, and I'll show you some examples, we will actually make the assembly, we'll compile it, and then we'll see how we can test it in WinDebug. So if you've never written assembly before, that's fine. We'll write the code here in Sublime, and you'll have access to an environment that is extremely similar to what you're seeing right now. You'll be able to use NASM to compile the assembly. We'll have special scripts that you can make use of to take the assembly that has been compiled and then extract the opcodes, and then you can take those opcodes and we can insert them into a tester program, and that tester program will automatically insert a breakpoint, and then there'll be a C program. We'll show you how to compile that here in Visual Studio using developer prompt. Once that has been compiled, then you can just load that into WinDebug. There will automatically be a breakpoint generated at the start of your shellcode. So you can just simply open it up in WinDebug, type G for go, and then it'll take you to right near the start of your shellcode, and then you can step through it line by line to make sure that it works as you intend for it to do so. Now that said, it's working in that environment. If you insert it inside a different application, sometimes there can be little nuances that may come into play, so just keep that in mind. But for our purposes in this lab, certainly it'll be a good exercise. So let's try to make sense of what we have going on here. So we have a bits 32. That just lets us know that, this is 32-bit. So when we compile it, then it takes care of that. Main entry point is a label. Call get EIP. Now this is the mechanism by which we get the absolute memory address, and we get that into EDX. So if I call EIP, then that means I will go to this label. Where is this label? Well, it's on the next line. So why would I do that? Well, the reason why is because it takes the address of the next instruction, this is something that call does, and it pushes it onto the stack. So I would get this address right here would be the next instruction that will be pushed on top of the stack. That's just something that call does. And then by doing pop EDX, I then get the base for that function, meaning what was on the stack from this is now in EDX. Right here, I do load effective address, LEE, and then I'm just making an adjustment for the first instruction. So just -5. And that should then get me over here. Or is it over here? Actually, I think it's right here, but when you actually look at it in WinDebug, it will be immediately obvious because it'll have the absolute label right next to it. So if it needs a slight adjustment, then that's the time in which you could make that adjustment. So right here we have a prologue. We move ESP to EBP, and then we make an adjustment on the stack so that we can have variables. So we generously give 1,000 hex. Now, some people have sometimes ran into issues with memory access violations. So if you're at a unique place, and this is not very common, it's not common at all, but it can come into play. So if you're a unique place in memory, and if you go -1,000 hex and that isn't readable or writable, then you'll get an access violation. So depending on where you are in memory at that point when this shellcode is being executed, you might need to tweak it. You might need to make some adjustments. If you're able to run shellcode, then you are in control. You don't need to do ROP. So if there is a specific memory address that you wanted to move the stack to, you could do that. So you could change the location of the stack to somewhere that is safe if there was a specific reason to do so. Well, for what we're doing right now, that doesn't come into play, but like I said, there could be special circumstances and special issues where that could be necessary. So let's try to make sense of this next bit here. So push EDX. This just means we're going to be using EDX. So we need to save that location. And then right here, the 0 hex, this is where we will put the hash, the module hash, which will generate that. I'll show you how to do that later on. And we'll put that hash there. So it could be just some D word, like kernel 32 4B 1FFE 8E. And then now we do call to get module address, so specific label. So what I like to do is just do Control F. And I can just hit my return button, and it takes me right over here to the get module address. So here, just like what it says, we're walking the PEB in order to get our target module. So where is the address of the target module? This is something that it'll take care of for us. And when it's done, it will return the module base address and EAX. And we need that. So that's the whole point, just to get that into EAX. And this right here builds off of what we saw in our last video. So I'm not going to explain everything line by line, just simply suffice it to say it is using those similar techniques. So our FS0 is the tib, FS30 is the PEB, we have our LDR, we go in there, we load a module, we can load a next module, and then here we have a module hash loop. So once we enter this here, we enter a label, we will keep on going in that label, and there'll be different things like absolute jumps, conditional jumps. We'll just keep on going until we get to the ret, because right now we're in a function because we took a call. Once we hit that ret, we return right back to right here, and then our next thing will be called pop edx. So we have that load SW, and so what we have going on here is we are just simply loading a word addressed to by the SI register into AX. Why is it SI? Why is it AX? Well, because it's word. It's not D for D word. It's not B for byte. It's just a word. Do we need to understand or care about this instruction or even this bit here? No, not really. So we have some checks here for the module. Once we get to our end hash check, then we are rotating left EDX by 7, so a bitwise operation, and then we're doing exclusive OR DL into AL, so we're just doing it 1 byte at a time. So in effect, we're modifying it one. You can kind of think of it as one character at a time, although that's not really accurate. And then we have an absolute jump, and so we'll just return to this location, and when it's done, then we'll get to the end module hash loop. That'll take us down over here. We can do a comparison with EDX and EBX. So when we go through and we do this part right here, we're generating a hash based off of each module that is loaded. We then compare it to EBX, and EBX is what we had loaded. So right here we would have put the hash that we want. So if there's a match on the hashes, then we're in good shape, and then we can continue on. That of course begs the question of, what if it's not a match? Well, we do our comparison there, so we're seeing if our EBX matches with EDX, and if it's not a match, we just go on up to our next module loop, which let's go ahead and get that in there. So then we just cycle through, we try out another module to test it. But if it is a match, then we're done. So that means we're done with that function. So we go back to where we were, which is not there, but actually get module address. And so then we have a pop EDX. So we're restoring what was over there in EDX, restoring that location, because prior to that we had pushed EDX. So we want to return it to its previous glory. Similar to that, we're going to save our base pointer, our EBP, and we are going to save our location, our EDX. So we go ahead and push them onto the stack. So our stack is a mechanism by which we save them. And then now we are moving our module hash, or actually not module hash, but our module address, because we get the return, we get it in EAX. And if we follow the logic of what happened in here, it's returned into EAX. So this is not the hash. I misspoke. It's the address. So we move that into EBP. And then now we have a load effective address ECI, load effective address EDI, and then we do EDX. So EDX is meaning an absolute location, plus the hash table. So EDX, we're able to get that to get us an absolute location, and then plus there to our hash table. Let's check that out. So it's a label. We don't need to worry about calculating. That's all taken care of. We just simply make use of the hash value. And then right in here we can add different values, such as for APIs. I don't recall what this is, if it even is something, and you could reverse it and figure it out if you wanted to. And at the end, so if we have a hash table, then we terminate it with this token, FF. So we absolutely need that in there. We also have a function table, and then this corresponds to location in here. So this is off just one. We add something else in there, we could make that 2 or 3. So let's go back over here. So we get those loaded. We load them into ESI, then into EDI, and then we make our call to get API address. So another function within our shellcode. This is just more of, now instead of peb walking, we're in the PE file format, and we are just walking that. So through here we go on down to the end of our optional header. We dereference that, we get that into EDX, that value. EBP is the base of whatever module we're looking at, the base address, so the kernel 32, for instance. And then from in there, we're now in the exports directory. And then we can access the function of names. We get that value. It's into EBX. We get the module address. We add them together. And now we zero out ECX. We load our API hash. So we save EDI, we save ESI, so that if they're damaged, we can restore them. We dereference ESI. We zero out ECX. We at this point we go and we load the API name, so we dereference EBX, moving it into EDI, and then we add that to EBP. We push EDX, then we zero out EDX. We do our create hash loop. So we take EDX, we're taking an API name, and then we just cycle through here. We have a loop to cycle through, and we go ahead and do the rotate left, and then exclusive OR by byte. And then once we encounter the null byte, then we're done. Then we can move that over into, or exchange it with EAX, or in other words, move it over. We pop EDX, or we exchange it with EAX. We do a comparison with EAX and ESI. So remember, what is ESI? Well, we can look up here and we can see it's our API hash. So we're checking to see if there's a match between the hash and what we just accessed. If it's not a match, that's okay. We just can continue on repeatedly until we do get a match. So right here, if it is a match, then we jump on down there. If it's not a match, that's okay. We'll just continue. We add 4 to our EBX, so we'll just go, and that's a D word. Remember, keep in mind each one of them is going to be a D word. We'll just cycle through it. But if it is a match, then we continue on down here. We load the API address, and so then we can make use of. We got the address of ordinals down there, right here. So we get the address of ordinals, and we can use that to find the actual API address. That's the purpose of that. But in any case, we continue on, and we just keep on going until we get to this instruction. So this is a store string instruction, and what it's going to do is it's going to take the value in EAX, because we've been working on EAX. EAX is going to have our final result. EAX is going to have the address of the API. Why do you care? Well, you care because the store SD is going to store that on over into EDI. Well, where is EDI? EDI points down to the functions table. So it doesn't really matter what you have down here originally, whether it's 1 or 5, or it's kind of arbitrary because it's going to get overwritten anyway. Because remember, right here, EDI. So we use this to store the values that we get. So however many different functions you have in here, you're going to need other locations for it down in the functions table. So there's a dichotomy between the hash table and the functions table. The only difference here is we have the token over here, our FF token, which comes into play right here. So you can have this token be anything you want, but we just use that to check to see if, do we load any more hashes or are we done? So this tells us that we're done and we can return out of this. So you can have as many functions as you want in here. And this is specific to different modules. So this is specific to kernel 32. If you find a function or an API that you want in a different module, and of course you can use MSDN to find out all this information, then you'll need another pair of hash table and function table. So the hash is your key into the function table, and then when this is all said and done, it will go and write that value for you over here, and you can use it. So let's go back to where we were. So we finished that up. When we ever have push or pops, we just unwind them in reverse order. So we did EDX last, now we do EDX first. We did EBP first, now we do it last. Those are now restored. And right here is the location where you can actually go and make use of your different API functions. So however many you discovered, whether it's 2 or 3, Um, Now, one thing that a lot of people need to do, and there's a good chance you may need to do this, is you may need to do a load library. So if you want to get a module that's not automatically loaded as part of the whatever application you're targeting, then you need to do a load library. So make sure, if that's the case, then load library is one of these guys down here, because then you can do load library here, supply it with the module name, and then you can repeat this to fill out the function table for that module. And we'll see an example of that. Let's go ahead and take a look at our script that we use to create the hashes. So let's pull that over here. And this is the script that takes two inputs on the command line. It takes the module name and the function name, and it gives you the appropriate output. So this is a Python script. I didn't write this. And let's get our word wrap on. So we have one to do the module hash, and then one to do the API hash. So you probably noticed the rotate left over there. You know, if you wanted to create your own script, that would be great. In fact, I'll probably make that an extra credit option, so that you can do something more original. Just remember that what you do here, you got to be able to replicate it over here. So in this case, and it also needs to logically work as well. We have some of these tokens over here that we saw over there. Do I want to spend any more time talking about this? Again, I'll probably give the option where if you wanted to create your own way of encrypting and decrypting and something like this, you could do so. The only gotcha is that when you get into the shellcode, it needs to not only you need to reverse it, but it also needs to work. So if you create your own and it screws up the code and it doesn't work, then absolutely it's not extra credit. It means that you can't get the assignment to work, and so that's a pretty serious problem. But as some people are more confident in their abilities, or more experienced, or just have a very strong enthusiasm for creating and doing things on their own. So I'll probably make that available as an option. But in any case, that's our script. So how do we run the script? Let's find out. I have this, of course, Sublime displays it up there. So I'll just navigate to where I have it. Oh, I'm missing one. And then this will be create hashes. So we do kernel32.dll, and we can do virtual alloc. And of course this needs to be, correct. If you do just one thing even a little bit off, then the hashes won't match. So that's something that you may need to do trial and error when you are developing this and you're using a WinDebug to check and see if things work correctly. But in any case, that gives us some hash values right there. So kernel 32 we could put right at that location. So I wanted to go through a couple examples here. And let's see if this matches up. We did our kernel 32. Yeah, that absolutely matches up. And this one is very, very simple. Now, if you do this, that's not going to work. It needs to be more complex than this, but that's okay. We're just doing this to get a feel for how we can actually implement it. So we have our kernel 32 here. We have our dual tables. And then everything else here is the same, except now we have Windows API pointed to it at EDX. Why is it EDX? Well, we can highlight EDX and we can backtrace it, and it says EDX is the base for the function. We get the absolute address into memory. We didn't know this before we did the get EIP routine. So we need that in order to access the kernel 32. Which if we go down there, we see it says 0. Why do we go to 0? Well, keep in mind, this is not 0. We had that store instruction where we copied the value that was in EAX on over to this location. It was pointed to at that time. It was pointed to by EDI. So this is not a 0. This is the location for WinExec. WinExec is an API that lives inside kernel 32. That's where it lives. And I see a hash there. So let's go ahead and let's see what happens if we do WinExec. And this does indeed match that. Some of the people might be thinking, well, what if I have WinExec or I have virtual alloc or virtual protect or get proc address? The length, the size of them are going to be different. How can it be that this is a D word? Keep in mind when you do a hash, this particular hash will always fit inside a D word. So the size or length of the API does not matter. Which, to me, that's obvious, but I just want to be abundantly clear to make sure everybody understands. So when we make the call to EDX plus this label, right now it says plus label. When you execute it in WinDebug, it's going to be plus some number. So the label here is just a human, nice little thing for the human. And then we do pop EAX. So why do we do push D word and then pop EAX? Well, we're getting this value, this D word, because remember, these are D words. This address right here is a D word. So we push it onto the stack. And then pop EAX means whatever is on top of the stack right now, which is this, because we just pushed it there, will now be moved into EAX. We then make a call to EAX. So we are calling WinExec. And that's all this does. It doesn't really do anything. So this is pretty dull and boring. I mean, you call WinExec, big deal. You're not doing anything. So think of the kinds of things that, if you were using Metasploit or MSF Venom, are you getting a shell? Are you causing something to be downloaded? What kinds of things do malware do that utilizes shellcode? Anything you can think of, you can do with the Windows APIs. You just need to identify which APIs, which parameters, and then call them in the correct order and do it correctly. So let's take a look at another example. So slightly more complicated example. These both use that same skeleton. We have our kernel 32. We have a kernel 32 hash table. Right now they're doing create directory. And they have calc. Now I don't recall, I know they go and find this, but I'm not sure if they actually, I don't think they actually used create directory. So it's there, but I don't think it's actually used, but that doesn't really matter necessarily. So we go through all this whole process again. We use our hash table to use it to populate the function tables. So these zeros become the correct addresses, and it just matches 1, 1, 2, 2. And then they also have exit process. They have calc exec, so they have the calc spelled out there. And that's one way to do it. Another way is we could just push the ASCII onto the stack and then use ESP as a pointer to that. So a couple of ways. We'll take a look at that way as well. We've already referenced that in our shellcode slides. So here we're calling calc exec. So what is calc exec? It looks like it's calc. So we get that. We just move ESI into that location. We push 0, and then we push calc exec, or just calc. We do that to, I guess, to give it the null byte or terminate it. And then over here we go ahead and we get the win exec. So we just call win exec. We push that, we pop it, we call it just the same as before. And that's all this does. It just executes the calculator. So nothing too exotic there. Let's take a look at another one. And this will probably be the last one that I show. I don't want to show too much because I want you guys to figure out on your own. That's part of the process, not just simply copying everything I do. But I want to give you enough of a background that you can really get a good feel for this and be able to do what you want to do and do what you need to do. So again, we have a kernel 32. We get the module address. We build out the function pointer table. Now we're doing the load library. I've talked about this before. So load library lives inside kernel 32. That's its home. It's been populated in the function table. We can do our restoration. We go to our starting address, and then we go and find the label for WS232, which is the name of a module, which is way down here. So we get that. We push that, and then we make the call to the load library. Notice that this call is different than some of the other ways in which we did it with the push and the pop. You know, there's room for creativity. It's however you want to do it, as long as it works. That's all I care about. So we push this. Now this has been loaded. We go ahead and we build out a function table for WS32. Let's go ahead and take a look at that. So they have a collection of different functions, APIs. What are they? What do they do? Well, this is part of what you guys will need to do, is you got to figure out, what do I need to do to use to do what I want to do? How do I use them in conjunction with one another? That's part of, you'll have to figure that out. I'm just helping you with the PEB walking and the PE file format, which is a very significant problem. The students who are taking this class and were in my reverse engineering course, They had to spend probably over the course of probably spent about 3 or 4 weeks on each part, but they had 3 different parts where they had to figure all that stuff out on their own. It's not a simple task and took a lot of effort, a lot of research. So I am doing quite a bit to help you with that. You just need to figure out which modules, which APIs, how do I connect them, what parameters do I do, how do I push them onto the stack, and you just do it through trial and error. You try something, you check it in WinDebug, you set breakpoints, you observe if it's having the desired effect. If it's not having the desired effect, then stop your WinDebug, go and make changes, and then try again. It's all you can do. So the hash table, the function tables, this will be populated. So 1, 1, 2, 2, 3, 3, 4, 4, our token. We have a command there. Now, as to how this individual is using these different things, that's something I'm not going to show because some of you may need to do this, and I want you to have the opportunity to figure it out. But as you can probably see in some of these, like this chunk right here, there can be a lot to it. But it's just essentially pushing things onto the stack, and then once you get things pushed onto the stack, then you make the call. Here's another example we have. I don't wish to show the entire thing, I just wish to highlight a different technique. So if you don't want to have words such as, in this case, URL mon, which is a module, if you don't want to have that down here at the bottom, you can just push those names onto the stack. You just need to be cognizant of little Indianness. So here we're doing on. So let's actually go back here. So ECX, we zero that out. That means it's all zeros. Because if you do exclusive OR for one register by another register, it's 0. That's the result. So the entire register is 8 zeros. We move into the lower, ECX is the lower 2 bytes of ECX. So we move that over there. So it was 0. We move the on over there. We push that onto the stack. And then we do our URL mon. And we push that. Actually, yeah, we push that onto the stack. And so now and now we can't just leave it there. We need the address for that. If we left it here, it's going to interpret this right here as an address. This is not an address. This is URL mon in little Indianness. So ESP is the address that points to this location on the stack. So it'll go to this location, it'll read right here, and it will read right here until it gets to the null byte. And then it'll stop. So that's why we push ESP, because here ESP, which is the address to this, is our argument. Let's take a look here at this. So I moved on over to this website. You can pick out whichever one you like. And I have this first little chunk right here, which is the first thing we pushed onto the stack. And then this second one, and it's in little Indianness. So the first thing I did was no, and then MLRU, which reads URL, and then mon, URL mon, which is the name. So we do this in reverse order, a little Indianness. So, 6E, 6F, etc., etc. If you don't do it this way, it's not going to work. When you do the push ESP, it would just be in reverse. We don't want it in reverse, so we have to provide it in reverse due to little Indianness. If this is too confusing, you can do it with the other technique where you have the variable or the dB down at the bottom. This is just another way to do it more directly, just pushing the stack up, or the ASCII onto the stack. So I think that's good for the examples that I wanted to provide, to give you enough opportunity so that you can have your own opportunity to experiment and to be creative. Let's take a look at some of the tools that we can use to get some of this working properly. So which one was this? Was this the really super basic one? Well, one of them at least. So how do we manage all this? So I have in here, you go down here, and this should be the same in your guys' IA lab. If you're working in your own system, then it's up to you to install whatever you need, and you'll just be on your own for that. Here I have NASM. I go to the NASM shell, which I already have open, so I'm just going to go there. I have various different ones. So we're going to take a look here at number 1. So I just do NASM, and then I can do 1.asm. I do my output. I'll call this, let's call it S1, and I just do .bin. And I can check here, and it's right there. So I was successful. Now we'll also take a look at some other scripts that are going to help us. Because our job is not to write assembly, our job is to write shellcode. So as long as we have our bits 32 and it's correct assembly, it'll compile to a bin. That's all you need to do, is just use NASM just like that. So it's that simple command right there. That's all I want you to do with NASM. If you know how to do more, do other things, that's fine. I don't really care. We just need it to compile into a bin. So then we go on over here to this read bin file. It reads a bin, so it needs to be a bin. That is important. It's written by Peter Van Eckhout. He's the creator of the Mona Python script, as well as the creator of the Corelland website with many great tutorials. It's a Perl script. Takes a bin and it outputs it with bytes that we can drop inside various types of exploits. So we can go check that out. As best, just don't need to understand it or to even really know Perl, just simply to results. So we're in the correct directory, so let's go ahead and use it. We do Perl PVE. I've moved the file over here into the path, and that's what it does. So if I were to open this inside of Sublime, we see this representation, which is a little bit very similar. It just goes and takes this and adds the appropriate things so that we can drop it into different things. So if you wanted to drop this shellcode that you created, then you could drop that into your exploit, and you'll have the opportunity to do so. I'm also providing you with another tool that you can use in order to test it outside of an exploit. So it's the SC test offset. And what this does here is, let's go through this here. So we put our shellcode right here. Did I save it? So as long as you don't need, actually need, with Sigwin you don't even need to copy and paste. If I just go like this, I've already copied it. So I paste it there. I had the semicolon here. I was sure to get that, and so now the semicolon is over here. So my shellcode is right here. I make an int I 0, a length 0, target address 0, target address, then offset 0. If you were taking a look at something, and I mean, of course you could probably even do this with shellcode that you do, like if you wanted to be really clever and you wanted the offset to start at a certain location and you figure out how to do that, you could do that. That is a technique that malware uses, so the offset to start might be somewhere in here. So you could calculate that offset and put that there. In this case, the offset is 0, so you don't need to worry about any of this here. We had allocation of 1,000, so if it's some huge giant thing, then you might need to increase it. We get the length of the shellcode. We do a mem move. Mem move is an API that we've talked about. So here we can see it in action in actual C code. So mem move is a stage which we do a virtual alloc that creates a memory of region, and it does a boolean to see if it's correct. And also if we set it equal to, then that'll give us the address of it. So this is the location that we've allocated. We take our shellcode, we move the shellcode over there. The mem move tells us how much do we move. We move 1,000. So now this shellcode right here has been moved into a location that has been created with virtual alloc. We have a target ADDI, which we go and get the stage. So the stage will be 0. And then we plus our offset, which in this case is 0, but if your offset to start was over at 8B, then you would need to adjust that. We see also the 40 hex there, so that means RWX, read write executable. Now we have inline assembly. We have an int3, so int3 inserts a software breakpoint. I don't know a way to do this outside of assembly. If you do know a way, to let me know. I don't think it's possible though. But if you have a high-level language that can accept inline assembly, such as C in Visual Studio, then you can make use of that instruction and you can have that desired effect. We have the target address, so we have the memory address. We move that into EAX. We do a jump EAX. So now we're jumping to wherever the shellcode is, and then we can start executing it. So the int3 is our breakpoint. So you run this program. You want to run it inside a debugger. You don't do it outside of a debugger. It's not designed to do that. If you have an int3, that's going to give you problems. You only do int3 when you're doing something inside a debugger. So we'll have a breakpoint that'll stop right here. I mean, I guess you could, well, yeah, right there is really the only place that it really fits. And then you can just step through here, and then you'll be right here. So you can test your shellcode in this kind of a harness, if you will, to see if it works correctly. And as I mentioned before, there can also be, sometimes certain applications have special circumstances, so don't assume what is true in this application isn't necessarily true. There could be some weird nuances. But as you're developing this could be something to maybe get you started. But then you may want to adapt it to the actual program that you're doing. So I've saved this. How do I use it? This is just C. Well, the first step is to hit save. Big surprise. And then let's clear this out. And it's in the lab files. I didn't mean to save this, but let's save this as tester2. So I just do, to use developer prompt, you go here, you type develop, and you click on that. That's all you got to do. Oh, my escape is not the spot I'm used to. So now I just do the name, cycle through these, or I guess tester 2. It has compiled it. If you get to this stage where you see the out and then the object, the executable, that means it was successful. So even though it gives you a warning here, you can ignore that. If you don't get to this stage, then it didn't work. And you can always just test to see if the file exists, and it's right there. So now I can do WinDebug and tester 2.eax. We'll open it on up inside our WinDebug. It automatically inserts an int3, which is a software breakpoint. Anything you open in WinDebug, we don't care about that. We want to get to the one that we created. We type G for go. It'll say busy for a little while. I'm not sure why it's taking so long, but eventually it gets us there. And we see that our move D word EBP plus 8. Well, why is it EBP plus 8? It's just because it's a variable. That's how we represent our variables. We're going to step into and step into. Now we're going to jump to EAX. So we see the address there, which is like 30,000. And now it says call 30,005. Why is it 30,005? Wrong one here. Because it's call a label. I do +5 or -5. And if you calculate that location, it's going to be right here. Why is it 5? Well, you just count up how many opcodes there are. However many opcodes are needed to perform this instruction. x86 is variable length instruction, so some lines can be long, like this. Other lines can be really short. That's one of the reasons why with ROP you can have your opcode splitting, because unlike some other architectures where they have enforced alignment, our alignment is not enforced. It's variable length. So we make the call to that location, then we do load effective address. We're making an adjustment. So this address right here, we adjust it. It was 5, so we're taking away 5. And then that will be loaded, that address will be loaded into EDX with our load effective address. And then we push that onto the stack with EDX. And so EDX gets us the absolute address. So right there, 3,000, we have it. Let's continue on. So we get to a call, and it takes us all the way down to that call. So we're not going to obviously go through this line by line. I'm just showing you how do you go through and test it, because you will need to test it to make sure it is correct. One other thing that I probably should, well, I guess we could do a little quick review here, is we could scroll on down and we could, let's go down over here to, we could do return to cursor. And let's do a return to cursor here. And I'm just trying to get past all these rets. So I want to, I guess I went so far, it was a very simple one. But what I had wanted to do was if we have a call like this, and this is a very simple one, but if you already know what's going on in some of these preset subroutines, these preset functions, you don't want to go through the whole thing, do the step over. So the step over, when you get to a call, it'll just skip past the whole thing. It'll execute everything in there, and then it'll stop at the next instruction. So step into, you go and execute each and every instruction. Step over is exactly the same, each and every instruction, except when you get to a call, instead of going inside it, it just skips over it. I mean, it doesn't skip over it, it still executes everything in it. You just don't have to wait through that, which is really useful if you have very elaborate function calls that you don't care about. So we have a calculator execute, so that's great. So again, all we need here is we need to go and write our shellcode. Then we go to our NASM, we compile it, we get the bin, we go over, use the Perl script, we get this, and then we can, I had it somewhere over here, we can add it to the tester, save it, and then we go and compile it with our CL. You can ignore all that as long as it gets you those last two lines. And then we just simply do WinDebug and then the name of the executable. And then we can step through it line by line to check to make sure it works. And if that is the case, then we can actually put it inside our real exploit. Of course, for what I will have you do, I will also give you an option to, which I strongly encourage but don't require, where you can encrypt your shellcode. One good reason why is no bytes. I don't know, I might even require it. Haven't really decided. So I may actually just require it. So if you go back to our shellcode where the slides, I'll talk about some different ways where you can take shellcode like this. You can develop an algorithm to encrypt it. It could be, for instance, going through and doing exclusive OR. So I say, let's do exclusive OR on each and every one of these bytes. And then I'll have a new chunk of shellcode. It'll be the same size. And then this would be, you'd have a decoder at the top, and then it would go down and it would modify this byte by byte, decoding it, restoring it to what you see. That way you could have no bytes there. And not only that, it would be slightly less obvious. And if you develop an encoder, I mean, really there's no limit to how many times you could decode it. You could encode it multiple times, multiple different ways. I'm not really sure. I'm not an expert on developing encoders. So if you wanted to exclude particular bytes, I'm not sure how you could do that, but I don't require that. Alrighty, that's all we have for our video today. Very soon I will introduce a lab exercise that will incorporate much of what we talked about. So should be a fun, exciting time to get our hands dirty with shellcode. If you haven't used assembly in a long time, that's okay. You're not really doing much with assembly. You're just using a skeleton and you're just pushing things onto the stack and making some calls. So it's not as difficult as it may sound, as long as you can understand what we've talked about today. Even if you've never done anything like this, or you haven't done shellcode or assembly in a long time, or maybe you've never done assembly, which I think there are one or two people, that should be fine. You should still be in good shape. So, alrighty, I'll talk to you guys later.